This video is from noatom.com. Hi everyone, this is Josh Yu, Justin Yep, Alex Ihlenburg, and Ashley Church, and we are group B29. Today we will be discussing special types of graphs, their definitions, and providing a few examples. Before we begin, we will explain some graph terminology that will be used throughout the video. Graphs are made from the following form. There's a vertex, which is the nodes or the points, an edge, which is the line connecting the vertices. It can be directed or undirected. There are loops, which are edges that connect to the vertex itself. And vertices connected to one another by an edge are known as adjacent. Graphs can be made in an infinite number of ways. They can be simple, which means there's just one edge between a pair of vertices. Or we have multigraphs, which means there's multiple edges connecting a pair of vertices. A path is just a sequence of vertices such that from each of its vertices there is an edge to the next vertex in the sequence. This can be infinite or finite. First we have an empty graph, which consists of n vertices and there are no edges. So that would just be some vertices with no edges connecting them. Next we have complete graphs, which are denoted by K sub n, and it is a simple graph that contains exactly one edge between each pair of vertices. So this here would be K sub 4. Next we have cycles, which is a path such that the start vertex and end vertex are the same. These are denoted by C sub n, and n must be greater than or equal to 3. We have bipartite graphs. Sometimes a graph's vertex can be divided into two disjoint subsets where each edge connects a vertex in one of the subsets to the other. This is known as a bipartite and is defined as the following. If the vertex set V can be partitioned into two disjoint sets V1 and V2 such that every edge in the graph connects a vertex in V1 and a vertex of V2. Also, a simple graph is bipartite if and only if it is possible to assign one of two different colors to each vertex of the graph so that no two adjacent vertices are assigned to the same color. These are useful as models for problems that require matching elements from one set to another. And here is an example of what a bipartite graph would look like. And as we connect them, you can see that no two colors are touching each other. Therefore, it is a bipartite graph. Next we have complete bipartite graphs. Going off from a bipartite graph, there is a complete bipartite graph, which is a graph that has its vertex set partitioned into two subsets, M and N vertices, with an edge between two vertices if and only if one vertex is in its first subset and the other vertex is in the second subset. This is denoted as K sub mn. Here's an example of what that would look like. This would be denoted as K sub 3, 4. Next we have regular graphs. A regular graph is very simple. It is just that each vertex has the same adjacencies. Regular graphs come in many forms. For every n vertices, there are multiple ways to draw a regular graph. Here is some pictures of regular graphs taken from wikipedia.com. For every n vertices of regular graphs, they are given specific names. Here are some of the names: cubic graph, quartic, quintic, sextic, and so on. Next, we have a Boolean cube. You can see from the truth table on the left that it corresponds to the Boolean cube on the right. Next, we have planar graphs, which are defined as graphs that can be drawn in the plane without any edges intersecting. They are important for the design of electronic circuits or road networks. Also, they are important in understanding concepts such as Euler and Hamiltonian paths. This is an example of a planar. And next is an example of a non-planar. We can see that the second one is non-planar because the edges on the inside intersect at points which are not vertices. Our last example shows how assigning colors makes it easier to visualize adjacencies in graphs. They are called K-colorable graphs. To color a simple graph, every vertex must be assigned a color so that no two adjacent vertices are assigned the same color. K sub n can be represented using no less than K sub n colors. However, it is important to note that for planar graphs, since their lines do not intersect, the chromatic number is no greater than 4. They are useful for scheduling and assignment problems. This is an example of a K-colorable graph, and here in this one we have 3 colors. Understanding graphs is an integral part for problem solving for both theoretical and real-world situations. Special graphs are especially important because they arise in many types of situations and have unique properties. In conclusion, when studying graph theory, it is important to recognize these special graphs as much as the others. For more videos on discrete mathematics, you can go to noatom.com.